Welcome participants again to the second session. Today we are having with us Bora sir. Bora sir is professor in Department of Electronics and Electrical Engineering, IIT Gauhati, and he is a very renowned person and very knowledgeable, plus very kind-hearted person, and we know him since our college days. And sir is has a research interest in computer vision, pattern recognition, video encoding, image and video watermarking, perceptual video hashing, signal processing, and communications. Previously, sir worked in AEC Gauhati, Assam Engineering College, also in Gauhati Engineering College. He was a faculty member, and in Gauhati University also he was a faculty member. Sir had his ME and PhD degrees from IISc, and we are very much thankful to him that he has given his consent to join our workshop. And I hope all the participants will learn a lot from him. So, sir, I welcome you on behalf of Department of ECE and Gauhati University as a whole. So, without making any further delay, I hand over you the stage. Very welcome, sir.
Yeah, okay. Thank you, Jyoti, and welcome the participants. So I'll tell about artificial intelligence in healthcare from expert systems to deep learning. Okay, and my plan of talk is like this. Expert systems in healthcare, traditional expert systems, machine learning approaches, artificial neural network, deep learning, convolutional neural network, healthcare application, our work on retinal images. Little bit I'll tell. Okay. My lecture. Okay. So this is the outline. You know, artificial intelligence is the use of computer-aided methods to perform tasks normally requiring human intelligence, such as visual perception, recognition, and decision making. We know that these are the hallmark of human body, but we want to impart those qualities to machine. In healthcare domain, AI systems have the potential to support physicians in clinical decision making, enhance primary care through chatbots, aid robotic surgeries, provide virtual nursing, aid in the accurate diagnosis, etc. So in all these respects, AI has played their its definite roles. Okay. First, let me tell about what is an expert system. That is a traditional expert system. An expert system is a computer-based decision-making system that performs the task normally performed by a human expert. Expert systems are designed to solve complex problems by reasoning through bodies of knowledge represented mainly as if-then rules. Now it is expert system is based on knowledge. That is one important aspect. An expert system generally includes three components. A knowledge base, this is the knowledge base, and knowledge is acquired from the experts. A rule-based inference engine, so on the basis of the knowledge and on the basis of the query data, inference will be made. Okay, and that inference engine is rule-based. Okay, and a user interface. This is a crucial part. This interface will take the query from the user, and also through this interface, advice will be passed to the user. So that way, one important aspect is that here knowledge is stored. Knowledge from the experts is stored in the form of if-then rule, represented mainly as if-then rules. There are other representations. Now, diagnostic expert-based systems are computer systems that seek to emulate the diagnostic decision-making ability of human experts. So, expert systems were greatly applied, like in addition to other applications, it was applied to medical system. Medical expert systems generally include a knowledge base which encapsulates the evidence-based medical knowledge that is curated by the experts. A rule-based inference engine devised by the expert which operates on the knowledge base to generate different diagnoses. A user interface. These are the three parts of traditional expert systems. Diagnostic knowledge base generally consists of diseases, findings means symptoms, signs, history, or lab results, and their relationships. In many cases, they explicitly lay out the relationships between set of findings, that is, symptoms, signs, history, or lab results, and the cause of them disease. So, suppose symptoms is given, what is the cause? So that information is stored in the knowledge base. Examples of expert systems for healthcare. Some of notable systems include MySyn, Stanford University, early 1970s, diagnosed for infectious diseases and suggested drug to treat infection. Internist One, University of Pittsburgh, that is also early 70s, provided diagnosis in internal medicine. The users entirely entered findings means those symptoms, etc., and system produced diagnosis. Quick medical reference, QMR, University of Pittsburgh, 1980, is used to help diagnose adult disease by providing access to information about the most common diseases, including medical histories, symptoms, physical signs, and laboratory test results. DXplain, developed at Massachusetts General Hospital 1987, accepts a set of clinical findings to produce ranked list of diagnoses which might explain or be associated with the clinical manifestation. Okay, so that way many traditional expert systems are there in the healthcare domain, but what are their limitations? The maintenance of expert systems requires a dedicated team of experts who continually monitor and reconcile new research. It may take several years for a newly identified disease to be part of the expert system, as it may be costly to run medical studies. An inference engine based on an underlying knowledge base is devised with the assumption that it will be used in noise-free environment. Okay, so that is any different environment, the inference engine may fail. So that way, the traditional expert systems are very limited. Now, why it is limited? Expert systems are examples of knowledge-driven system, and it is very difficult to store or interpret knowledge. So that way, expert system, though they were popular, now they are not so. Today's AI is data-driven. It involves collecting data, extracting patterns, and making human-like decisions. So that is important for today's AI. Machine learning plays the vital role in the data-driven system. So that way, with the advent of machine learning and particularly deep learning, the entire paradigm of expert system has changed. Now it is more data-driven than knowledge-driven. Okay. Now, so this is the introduction about the expert system, what expert system does, and how expert system is made. Now we will go to some modern day, suppose expert system with the advent of machine learning and deep learning, how AI has come up to take a vital role in the diagnostic system. Modern day AI has greatly popularized two words, machine learning and deep learning. DL will abbreviate as ML and DL. These algorithms have enabled researchers and developers to gain deeper insight from the enormous amount of data available and achieve superior success in many tasks. So nowadays, because of the development of electronics particularly, we get enormous volume of audio-visual data. So from those data, patterns may be discovered or obtained through machine learning algorithms, and that can be used for different tasks. So that way, if we consider AI is a broad area, machine learning is a subset of it, deep learning is a subset of machine learning. Okay. Now let me tell something about machine learning. Machine learning is a branch of AI concerned with the design and development of algorithms that allow computers to evolve behaviors based on empirical data. So it is a branch of AI, and it is concerned with design and development algorithms that allow computers to evolve behaviors based on empirical data. Arthur Samuel, a computer scientist who popularized the term machine learning in 1959, defined it as the field of study that gives the computers the ability to learn without being explicitly programmed. In machine learning, we generally provide data with or without levels. The machine trains itself to learn its own logic, which will be evaluated during testing. To facilitate learning, handcrafted features are extracted from input data. From these features, the algorithm will learn and learn the similarities and dissimilarities among data points. So that way, machine learning algorithm first pre-processing task is feature extraction. These are normally through some algorithm or different ways of feature extraction are there. Different features are there. Those features are fed to will be fed to ML algorithm, and the algorithm may group the objects corresponding to the features, or it may be used for prediction. So that way, this is classification, and this task is known as regression. So regression, so classification, for example, maybe you want to classify between dog and cat, very simple example. Similarly, prediction, you may continuously predict the, for example, temperature data. Okay. So that way, essentially, in traditional machine learning, there is a step of feature extraction. That is the handcrafted feature. That's why it is called. And then those features are used by the machine learning algorithm. For example, maybe neural network or support vector machine for classification or regression. Now, broadly, there are three types of learning algorithms. Supervised learning, a level is provided for each input, and the model will learn a mapping from the inputs to the levels. and tries to achieve desired level of prediction of accuracy on testing data. That is supervised learning. Unsupervised learning, no level is provided for input data, and the model tries to cluster the input data based on similarities among them. Suppose you are given some simple case, suppose scores of a cricketer. So if we cluster those scores, maybe we can arrive at two classes, maybe that one class for batsmen who scores high, one class for bowlers who scores less. That way, that pattern will be found out in an unsupervised manner. But in supervised manners, already we have level data and we'll be training, and during training that model will be learned. Reinforcement learning, an agent interprets its environment. So agent is the decision maker who will give some decision, takes action, learn through trial and error. So if there is mistake, then there will be penalty. While training, the agent will be rewarded for desired behaviors and punished for undesired ones. In this way, reinforcement learning is done. So that were three types of learning. Now, what is deep learning? Deep learning algorithms form a subset of machine learning algorithms. When the data set is really big, ML algorithms are computationally expensive. Designing handcrafted features is also labor intensive and requires human supervision. DL algorithms can simultaneously learn feature and representations, not only feature, their representation, and perform tasks like classification or regression in an end-to-end manner. The advanced now lot of these deep learning algorithms are developed. There are maybe development may be traced because of two reasons. One is simpler algorithm, simpler mathematical operation based algorithm, like convolution is a simpler mathematical based algorithm. And also the advancement in the GPU technology led to faster adoption of deep neural networks as the computation time and cost to train image models on large amount of data is reduced considerably. Now, traditionally, this deep learning was developed on the basis on images, image or computer vision application. So as a result, that means the input to a deep learning algorithms usually is two-dimensional image or three-dimensional video. But gradually it started being applied to other multimedia applications, or now all sorts of applications. It can be applied to one-dimensional data, two-dimensional data, three-dimensional data, like that. But traditional deep learning based algorithms are based on two-dimensional data, two or three-dimensional data. DL algorithms are designed to extract information from data like the human brain from lower level to higher level abstraction. Okay, the network architecture generally have a layered structure of artificial neural networks that I'll be explaining, where initial layers learn low-level features and deeper layers learn high-level features. We'll be explaining that. For example, In image processing, lower layers may identify edges, while higher layers may identify concepts relevant to human vision, such as digits, relevant to a human, such as digits, letters, faces, etc. So, examples of deep neural network architectures are convolutional neural network, recurrent neural network, generative adversarial network, GAN, etc. Traditional machine learning versus deep learning. So traditional pattern recognition, fixed handcrafted feature that will be extracted, and trainable classifier. Okay. Midstream modern recognition, modern pattern recognition, that is unsupervised mid-level features. So from high level feature, that is low level features, mid-level features will be extracted, and that will be used for a used in a trainable classifier. But in deep learning, it will extract low level features, mid level features, high level features, and it is applied to trainable classifier, and we will get the classification result. So that way, this is the difference between deep learning and machine learning. These two parts are machine learning. This is deep learning. Now, so when we say about the classifier or even convolutional neural network or artificial neural network based classifiers, that is our goal of presentation here. The starting point is the perceptron. Perceptron. It was proposed long back, actually, even before coming of machine learning and AI. It was proposed. It is a mathematical function to model the biological neuron. So similar to processing, neural processing in the brain, now here also this basic unit will process. Okay, what type of processing is done? The mathematical function involves nonlinear mapping of the weighted sum of the inputs. So these are the input x1, x2 up to xn are the inputs. Each input is weighted by corresponding weight and then sum up. And there is some bias term is added, which can shift the input to some desired level. And then it is passed through a non-linearity. Okay. So this non-linearity, for example, it may be a sigmoidal non-linearity like this function. It will be, suppose all inputs will be mapped to this region between -1 and +1. So this sigmoidal is an example of non-linearity. And this non-linearity, why it is required? Because of this non-linearity now, it will be able to classify. So the perceptron weights are learned and the model is used as a linear classifier. Binary classification, only one perceptron can be used. But it cannot be used, suppose nonlinear classification. Therefore, initially people didn't know how to use perceptron further, but later on the concept of hidden layers and all those things will come, and so perceptron was developed into a very powerful computational paradigm called artificial neural network. Now this is artificial neural network, and these are nothing but perceptron actually. So an ANN is a collection of connected units of perceptrons called neurons. An ANN with many layers can learn nonlinear decision boundary. A single perceptron could learn only linear boundary, but an ANN with many layers can learn nonlinear decision boundaries. The ANN is trained using, okay. Now, in this case, this is the input layer, this is the output layer. Now you see that this input layer is connected to all the neurons in the next layer. Okay, this is connected, so that way it is fully connected. Okay, similarly this neuron is also connected to all the neurons in the next layer, like that. And this output layer, for example, in this case only one output suppose, then it is also connected to all the inputs in the previous, all the neurons in the previous layer. And there will be weights of each connection. Through this weight, neural ANN will, through the adjustment of the weight, the ANN will learn patterns. Now, the ANN is trained using a gradient descent algorithm applied to minimize a cost function. So that means suppose there is an output here and there is a desired output actually, and error between these two is represented in terms of a cost function, and the network parameters are adjusted. Network parameters means the weights of the connections are adjusted till we minimize the error. Okay, so this is done in the during training. So that way, ANN is nothing but a some combination of neurons in layers, different layers, and these neurons have connecting weights, and those connecting weights are to be found out, and that is by minimizing some cost function, and that minimization is done using a gradient descent algorithm. This is the basic algorithm used in all neural networks and even convolutional neural networks. Okay. Let me tell something about training using a gradient descent method. What is a gradient descent method? It is an iterative method. A new position vector is old position vector minus step length into gradient vector. That is the algorithm. Very simple algorithm. Since gradient of a function points to the direction of maximum increase of the function, so the negative of the gradient is the direction of maximum decrease of the function. Since our goal is to minimize, for example, it is a two-dimensional surface. If we want to minimize this, then we may apply this gradient descent algorithm. So we can start with any point here, and according to this algorithm, we will have to go along the direction of gradient. Now, what is gradient? I will be explaining mathematically. So that way, since the gradient of a function points to the direction of maximum increase of the function, the negative of the gradient is the direction of maximum decrease of the function. Therefore, in steepest descent algorithm, we always descend along the negative of the gradient. That is the idea. Okay, suppose I have somewhere here, this is the corresponding point. Now, what will be the next point? That will be decided by the gradient at this point. Gradient is, how gradient is defined, we will be seeing. We illustrate the application of steepest descent algorithm with the help of one example, a simple example, linear regression analysis. Okay, what is linear regression analysis? It learns a mapping function between input and output. X is the input, Y is the output, and these are data. Suppose corresponding to this value of X, this is the output. Some other value, this is the output, like that. So data are given. Now suppose we want some other point. Suppose at this point, suppose here, what will be the prediction? So the simplest function is the linear regression model, which y predict is equal to ax plus b. Suppose I want to fit a line between x data and y data. So that what is the purpose of this fitting of line? So that we later on, whatever some where data, suppose only x data is only given, y data we can immediately predict. Okay. Now this model is linear prediction model is y predicted is equal to ax plus b. This mapping function can be used to approximate the new value of x, new value for x. Suppose given x, what will be the new value of the prediction? Okay. Training the regression model involves finding out the best fit of the data. On the basis of the data, which line will fit best. Okay, this is achieved by minimizing the error between the predicted value y pred and the true value y. We generally minimize, in this case, minimization in terms of the sum square error. So we generally minimize the mean square error, MSE. What is MSE? So that is square error, you sum this square error. So yi minus corresponding prediction whole square, and then you sum up for all data divided by number of data. So that way MSE is equal to 1 by n summation of yi minus y pred I whole square, I going from 1 to n. So this is the, and in our case, this is a linear regression model. So that way, this is the mean square error. We substitute y predict I is equal to axi minus b. Axi plus b, with this minus sign comes here. Now this is a function. This is a cost function or a loss function. A loss function or a cost function which is to be minimized. Now we want to minimize this cost function, so that we will know this slope A and the intercept B. Suppose if I consider the extension of this line, that is B. So intercept B of the line, and if we know slope and intercept, then we can predict the value of y for all x. So a loss function or a cost function which is to be minimized. So this is the cost function. Okay. Now the partial derivative with respect to the parameters we will take. What is the partial derivative? So mean square error we have already taken. So here, suppose this is the mean square error. If we take the partial derivative with respect to A, then these two will come here, and then if I take the derivative with respect to A, AXI for AX from AXI, XI will come. So that way, this is the partial derivative with respect to A, and this is the partial derivative with respect to B. Now, when we represent these two partial derivatives in a vector, this is known as the gradient vector. So, gradient vector is the vector representing the first order partial derivative of the function. Here it is a cost function. So that way del MSC del A, del MSC del B, if we arrange it as a vector, that vector will be the gradient vector. Now what is the condition for a minimum? This should be equal to 0, del MSC del A should be equal to 0, and this quantity also should be equal to 0, del MSC del B is equal to 0. So from this we get one equation like this, and from this we get another equation like this, and solving 1 and 2 we can get A and B. That is the procedure. So in steepest descent, what it is done, how it is done, start with an initial point, A is equal to A old, B is equal to B old. That you can start with maybe 0, 0 or any other point. Then find the derivative with respect to the parameters like this, and update the parameters by this equation. A new is equal to A old minus mu times the partial derivative of mean square error at A is equal to A old and B is equal to B old, because here A and B are there, that we have to substitute whatever A old and B old we have taken, that will be substituted. Similarly, B new will be equal to B old minus mu times, mu is the step length parameter, into the partial derivative of mean square error at point with respect to B at point A old, B old. Okay, now that way we get the new point A new and B new, and this A new will be now A old and B new will be B old in the second iteration, and the whole operation will continue. So that way this is the initial point, suppose, and then after iteration we will get here, and then ultimately at convergence we should get this point. Okay, this is the basic steepest descent algorithm, which is the heart of any training process in a CNN or a neural network based algorithm. Okay, so that way we have learned the one of the important machine learning tool, that is artificial neural network, ANN, and we know that it performs a simple mathematical operation. What are those operations? That is weighted sum plus some bias, and then that quantity you have to pass through some non-linearity thresholding device. So we illustrated with the sigmoid non-linearity. Okay, and then the network, because the network will store pattern or store information about patterns in terms of those network weights, and those are obtained during training by applying some steepest descent algorithm on the basis of the error between target and the output of the network. Okay, but neural network is a generally you can say that it is a global feature-based network. Entire suppose image, if you are considering image, on the basis of that you get some features, and that is learned. From that features the network learn. Okay, so that way it learns global features, and also as dimension of the features increases, then the network dimension will also increase. But convolution network is shift from the this paradigm. So it is a stack of hidden layers is performing a nonlinear transformation. So this nonlinear transformation involves convolution and activation. So types of layers. So convolution. Suppose convolution layers, activation, pooling, fully connected. I will explain these layers. For example, this is the image. Suppose convolution and nonlinear mapping means activation will give these features. Again, from these features, we will get these features and these features, and then these features, whatever final features we get, that will be in a one-dimensional vector, and that will be passed through some full neural network, and you will decide whether it is cat or not. So what are the layers of a CNN? Convolution layer convolves a special small filter, that is kernel, with the input volume. If it is a multidimensional, means like suppose RGB image, in that case it will be volume. Otherwise we can consider different filters. That way also we can get volume. The kernel slides through the entire input dimension. Activation layer, the convolution outputs are non-linearly mapped using functions like rectified linear unit, ReLU, sigmoid, etc. I'll explain that. Pooling layer downsamples the output of the convolution layer to reduce computation. Two types of pooling, max pooling and average pooling. Oh, those will be, I'll be illustrating. Fully connected layer acts as a classifier where all the neurons are connected to all the input values. Basically, this is an ANN. Fully connected layer is an ANN classifier. Now, what are the components of a CNN? We already told that there is a convolutional layer. This layer is the core building block of the CNN that performs features extraction using the convolution operation. The layer is parameterized by learnable kernels, these are filters actually, that convolve over the height and width of the input to generate feature maps. Okay, the convolution with multiple learnable filters results in feature maps that represent different characteristics of the input tensors. Okay, the same input you can pass through different filters. Conventionally, multiple such convolution layers are cascaded. Okay, in a CNN to extract discriminative hierarchical features. So this is the cascading operation. So one filter after another. Suppose this feature map, again you are applying filter. Mathematically, for a input volume I, or in this case input image I, and convolutional kernel K, the output convolutional the output of the convolutional kernel is given by F0xy is equal to summation Sij I x minus I y minus j. So this is the convolution operation. So this is the filter weights. So the neighboring points x minus I, y minus I, j are the neighboring points of point xy. So all neighboring points are multiplied by the corresponding filter weights and then sum up. Thus the convolution operation extracts some local features from the data. For example, it may be the filter may be a low pass filter or high pass filter. Accordingly, some information about the image will be extracted, local information, because normally Sij uh, considered will be within a finite support corresponding to suppose FIR filter, finite impulse response filter, but here it is a non-causal type of filter because both positive and negative index will be used because image is two-dimensional and you can apply it from the middle point in all four directions you can take. That way it becomes non-causal. But only thing is that this filter you have to design properly depending on the application, what type of filter will be used. And this filter will extract local features from the data. For example, high level, if it is a high pass filter, uh, it will obtain information about age, etc. Okay, so essentially in convolutional neural network, a basic operation is convolution, which is done on a small patch, so that way this convolution operation extracts local information from the image. So we know what is a convolution layer. And then next term is pooling layer. Okay, activation layer I will be explaining. Activation functions are nonlinear transformation applied to outputs of a linear operator like convolution. Without nonlinear activations, the neural network would perform as a linear function only, so it will not be able to classify. The nonlinear elements allow for greater flexibility and creation of complex functions during learning process. Actually, during learning process, the network learns a complex representation, complex function representation. Complex means complicated actually in this. Here, representation for the data. Okay, so the nonlinear elements allow for greater flexibility and the creation of complex functions during the learning process. Now, some of the nonlinearity applied is sigmoid. So it is 1 divided by 1 plus e to the power minus x. Okay, so that way whatever data is there, it will be mapped to 0 to 1. Similarly, tan a, in the case of tan a activation function, so sigma x is equal to tan of hyperbolic x. So this will be data will be mapped between -1 and +1. Then this is a ReLU because it is linear, so that way it is easier to handle. A rectified linear unit. So here for negative input we get 0, for positive input we get the same value. So that way it is like a half-wave rectifier, rectified linear unit. And similarly, liquid yellow, there are other functions also there. Instead of 0 here, we'll put some small slope will be introduced. Okay, so these are some examples of activation function. Sigmoid, tanoid, ReLU, liquid ReLU, etc. are examples of activation functions. Next component is pooling layer. This layer fuses the neighborhood spatial information from the feature maps using average or maximum operation. So, in max pooling, suppose if it is a 2 by 2 window, from that only one value is, maximum value is taken, 23 here, 13 here, 17 here, and then 4 here. So that way we data are pulled actually into smaller dimensional image. Okay. Or we can take the average pooling instead of taking the maximum. We take the average. So average of this 2 by 2 window is 6. This is 13, like that. Okay. Pooling reduces the spatial resolution of the feature maps, thereby reducing the number of parameters and improving translation invariance. So that way pooling is done, and because of pooling now data will be less. There are other factors also, we will not bother about those things. Components of CNN, fully connected layer. The output feature maps of the fully final convolution or pooling layers are transformed into a one-dimensional vector. So this is an image actually. These image data are converted into a one-dimensional vector. This is known as flattening of data. The output feature maps of the final convolution or pooling layers are transformed into a one-dimensional vector and connected to one or more fully connected layers. These layers are dense layers where each node is connected to all the nodes in the previous layer by learnable weights. So basically it is a ANN. The final FC layer, also known as the output layer, contains the same number of neurons as the number of outputs categories with a softmax activation to obtain the class. If we are considering classification, then we can use an activation function, this type of activation function, softmax. Okay. Softmax is sigmoid type is a softmax. So basically our aim is to map into the range 0 to 1 so that we can interpret as probability. The final FC layer, also known as the output layer, contains the same number of neurons as the number of output categories with this softmax activation function to obtain the class probability. Okay. CNN classification, feature extraction we can represent like this. Is the composite function representing market. Hello? So where f is the composite function? Any question? Hello?
No, sir, there are no question, I hope.
Oh, okay. Feature extraction is done. Actually, CNN feature extraction is like this. We can represent it as a composite function like this, where f is a composite function representing the multiple linear and nonlinear layers of the CNN, and theta f represent the learnable parameters of the CNN until fully connected layers. Now, what are the learnable parameters? The weights of all the filters, whatever filters we are using in different layers, those are the learnable parameters. Output class probabilities are given as this: probability of C given x is the input, softmax of W0 y plus B0. B0 is the bias and this is the weight. The final class is given by this argument argmax. So for we'll give the level for which this probability is maximum. The model is trained with the because probability, so we can use some entropy measure as the cost function. The model is trained with the categorical cos entropy loss function for a set of training images labeled xm, ym. The loss function is given by this. So this is the probability of the classification, and this is the input categories that also model as a probability. It may be, suppose, given, suppose when ym is equal to c particular category, then it will be 1, otherwise it will be 0. So that way this part will have only 0 and 1 probabilities, and this part will have any probability between the 0 1, and between them we determine the entropy. So that way this is the way we determine the cost function. So once we define the cost function, against the best descent algorithm can be applied to find out the those filter weights and other bias parameters, etc. There are suppose CNN started with LINET because it is after Lee Kuhn, who was a electrical engineer, because convolution was familiar with electronics people or electrical people rather than computer people. So that way it started with LINET. Lee Kuhn was the inventor. First proposed CNN architecture, gave the standard CNN template, that is taking convolution and pooling layers alternately followed by fully connected layers. AlexNet proposed to use ReLU nonlinearity, which helps in train deeper nets. VGG16 proposed smaller filter sizes and increased number of filters as depth increases. InceptionNet proposed to use convolution to each convolution layer. This helps the network to learn more complex features. ResNet 50 proposed to use skip connections, which helps in training, because there are some problem in training CNN, because it is a very if it is very deep network, then steepest descent, when we find out this steepest descent through a mechanism called back propagation. So because of that, when we go deeper and deeper, this gradient value, sometimes it may vanish or sometimes it may explode. These two problems are there. These inherent problems are overcome in ResNet. By a mechanism called skip connections, we will not discuss in detail, and so on. Many other net, for example, ResNext and Google Net, many other nets are there. Okay. So that way we considered what is a CNN, convolutional neural network, and what is its architecture. The model has convolution as the basic operation, then nonlinearity, then pooling, and then finally fully connected layer. Other deep learning approaches are recurrent neural network, long short-term memory used for predicting future values in time series data. For example, optical character recognition application, this LSTM model is used. Autoencoder, because used to learning inherent low-dimensional structure present in data. So that way autoencoder. So from the data, volume of data, we will have a low-dimensional representation. Encoder decoder network used to pixel-wise classification of images or videos. The segmentation, for example, in segmentation task. Generative adversarial network, GAN. This is one important development. It can learn the probability distribution of the input data. Okay, and hence can generate a realistic looking artificial data. So that way, that is the importance of GAN. Okay. So next, I'll go. So that way we have discussed about uh, machine learning and deep learning approaches. Apart from the traditional expert-based system, now it is data-driven systems. Some of the application in healthcare, like disease diagnosis. This is an example of pneumonia detection. So different type of pathological images are given, X-ray images actually. From that, this network will be able to detect this on. Okay, this is the sex net. We have not given the architecture, but it will be able to detect particular pathology. Similarly, skin cancer detection. And this is arrhythmia detection, diabetic retinopathy detection. And this is eye image. So that way, different application we can apply deep learning. Now, another aspect is localization. Suppose when you are operating in brain surgery, where is the tumor? So that way, brain tumor segmentation. So you want to segment where is the tumor. So that way, that type of application it is applied. Similarly, organ segmentation, polyp segmentation. Polyps are some artificial growth in organs, harmless basically, but they may turn cancerous also. So this detection, for this detection also it is applied, localization. Okay. Now improve visualization. Suppose augmented reality microscope for cancer detection. So that way, initially suppose resolution is less, but that you can through deep learning technique you can increase the resolution. Super resolution of knee MRI image, for example. So this is the low resolution image. So artificially it is super resolved to high resolution. Similarly, OCT denoising, I'll explain. So that way denoising will improve visualization. This is this part noisy, this is less noisy. Okay. So that way different applications are there. Similarly, another application is for deep learning for healthcare, that is surgery application, surgical tool identification out of different tools. The surgeon has to identify the tools, so that way this is one approach, surgery phase identification. Then surgical skill assessment, even whether it is surgeon's surgical skill is good or not, that also can be assessed using deep learning based approach. Okay, so that way there are different healthcare areas where deep learning is applied. Okay, but we will be particularly concerned with one specialized area, that is CNN for automated retinal image classification. You know, retina is the part in the back of the eye where actual image is captured, and it is the retina is basically a part of the brain. So, and retina captures information about the 3D world. Most of retinal diseases such as age-related macular degeneration (AMD) and diabetic macular edema (DME) are progressive in nature. AMD and DME affect nearly 8% of the world population. According to National Eye Institute USA, the prevalence is estimated to increase. This is 2030. Early diagnosis of the retinal disease play a crucial role in the prevention of blindness and controlling the progression of the disease. Automated disease diagnosis methods have the potential to improve diagnostic accuracy, help in fast screening, save numerous clinical hours of medical practitioners, enable semi-skilled medical professions to perform mass screening of at remote locations. Telemedicine application basically. So if the suppose somehow that image or retinal image or some other information are made available, and from that screening can be done at least in the first level, whether it is a pathological case or a healthy case, that can be obtained. Retinal imaging modalities. There are three basic modalities: fundus photography, the fundus camera, and fluorescent angiography with the help of some dye, and OCT, optical coherent tomography. That is our main concern. So it is unlike suppose in fundus photography and fluorescent angiography provide 2D and face view of the retina. OCT provides non-invasive in situ 3D visualization of the retinal microstructures. Okay, so that way it is tomography because it is reconstructed into section and volumes. So that way it provides non-invasive in situ 3D visualization of the retinal microstructures. More clinical information. OCT contain more clinical information compared to fundus photography and fluorescent angiography. Okay, useful for early diagnosis. Okay, diagnosis of AMD and DME using OCT B scan. So OCT scans are normally A scan, which is a one line, B scan, which is an image of a layer in the form of image, and then this stack of images will give you the volume. So that way different diseases can be identified from the OCT B scans. These are illustrated here. This is normal image. B shows the pathological manifestation in AMD, partial drusen by asterisks, geographic atrophy by brackets, and fluid deposits by solid arrow. Different disease conditions are represented. So it can be done through, because images of different layers are possible through OCT, so it can be identified more precisely compared to fundus or angiography image. Now, how to apply suppose diagnosis of particular disease from B scans? What we will do? We can extract feature extraction based method. These methods extract informative features from the pathological biomarkers of the OCT images, pre-processing, denoising, lateral segmentation, image cropping, threatening. These are to be done. Feature extraction, like maybe these are very traditional mid-level features. Classifier, SPM, base classifier, random forest classifier, etc. Input OCT image, reprocessing, feature extraction, classifier. So disadvantage, what is dependence of domain on domain experts, sophisticated pre-processing, limited feature extraction capability. Because OCT image is also a low resolution image, so that way feature extraction is difficult. Transfer learning based methods. Transfer learning is a technique where a model learned in one setting is exploited to improve generalization in another setting. So maybe some low-level features will be learned from another setting, but high-level features will be learned from this specific data. Transfer learning allows using a network with fixed weights adapted from practical domain at the low levels and retrain at the high levels to learn distinguishing features specific to the task. Okay. Popular use models are AlexNet, BGG16, BGG19, ResNet, etc. Advantages: a good way to exploit advantages of deep learning with limited dataset. Disadvantage, as the pre-trained network are learned from natural images, understanding of the behavior of the filter output is inscrutable for medical images. This is the disadvantage. Fully trained single stream CNN models in this category use single stream CNN trained end-to-end for classification of OCT image, network, sequence of convolution, batch normalization. These are techniques, real loop, pooling, followed by a fully connected layer with softmax activation. Methods, OCT net, this is in this reference, iterative feature fusion, CNN, iterative feature fusion, CNN, etc. Okay, these are some approaches. Multi-scale or multi-stream models. The retinal disease widely vary in terms of shape, size, texture, and spatial location and severity stages. The single stream CNN may not be adequate. This is the single stream CNN. This may not be adequate for effectively representing the diverse multi-scale pathological characteristics of retinal diseases. Therefore, various multi-scale approaches are proposed. Okay, so at different scale, actually, different diseases may be more prominent. Okay, and this is one of our approach. So multi-scale, multi-stream models, multi-scale deep feature fusion. The method uses multi-scale, this one, multi-stream model. Okay. To extract, this is multi-scale spatial pyramid. To extract multi-scale features from the OCT images, multiple CNNs are used to extract features from the multi-scale images. These features are used to obtain high-level multi-scale features for classification. Okay, so this is like multi-scale spatial pyramid decomposition. Just like in image decomposition, this is the decomposition, and then to each decomposition we apply CNN like that. Then these features are fusion of features, and then it is used for classification of three classes basically, the AMD, DME, normal, like that. So this is an example of multi-scale pyramidal decomposition. Okay. So this is one approach. Another approach is attention-based OCT scan classification. Instead of visualizing the attentive regions of the OCT images during the testing phases, it would be imperative to constrain the network to pay attention to the clinically significant regions during training for improved learning of disease features. So that is, there are different attention models are there. During training itself, you should give attention to some area of special interest. That way, attention has very wide application. For example, language processing. Similarly, attention models have been applied for medical image applications where clinically important regions are given more importance. The attention-based models have been used to provide selective focus on the clinically relevant regions of the OCT images to acquire discriminative features representation, thereby boosting the recognition performance. The lesion-aware CNN, LACNN 34 simulates the ophthalmologist diagnosis that focuses on local lesion-related regions when analyzing the OCT image using the attention mechanism. So there are this is the input image, CNN, convolutional feature maps will be obtained, and this is the network which will give the attention map, and this features will be multiplied. So this is the weighted feature map. Okay. So one is weighted version, other one is simple output, and this way we get this new set of feature map, what is known as. But how to detect those attention maps? That is, there are different algorithms are there. So during training, that attention map will be obtained, and that way we will get the lesion-aware feature maps, and then pooling convolution. This way, this process will be again continued, and finally, there will be fully connected layer will be there, and classification will be done. Okay, so this is attention-based OCT scan classification. This is another method, generative adversarial network for classification with limited data sets. The deep learning models require a large amount of level data during training for reasonable good classification performance. It is difficult to acquire a large amount of OCT data at early stages as the diseases are asymptomatic in nature. Also, leveling of large amount of OCT images is cumbersome and expensive. Therefore, data-efficient classification frameworks that can perform efficient classification with limited level data are desired. Recently, semi-supervised generative semi-supervised generative adversarial network are used for this task. Okay. So this is there is two data. One is real data. Another one is artificially generated data, and from that it is classification. Okay. So semi-supervised again for OCT classification. So this is the mechanism for generating the data, and this data can be used to train. Because at one stage, suppose the network will reach a stage when there the network learns the distribution of this data, so that way OCT data will be generated and that can be used for training. Next problem is OCT volume classification. OCT B-scan classification are appropriate for preliminary diagnosis and mass screening application where quick diagnosis results are desired. However, it is challenging to identify the retinal region for screening to capture the pathological manifestation for diagnosis. Such selection requires clinical expertise and may be subjected to inter and intra-observer variations. Moreover, the clinicians mostly prefer the OCT volumes over single B scans for a comprehensive analysis of the spread and severity of diseases. The volumetric OCT data constructed from a collection of densely sampled B scans are more suitable as they scan over a large retinal region. So the automated classification of OCT volumes can result in a comprehensive and reliable diagnostic tool for medical practitioners. So that is the goal. So this is the procedure. B-scan attentive CNN for OCT volume classification. In clinical practice, the ophthalmologist identify the salient B-scans with disease manifestation and fuse the clinical information from these scans to diagnose the disease and their severity stages. Therefore, the proposed that is B-scan attentive CNN, we name it as BSCNN, automatically encodes the discriminative information from clinically relevant B scans to make diagnosis decision for volumes using the attention mechanism. Okay, so this is like input OCT volume, B scan extraction, and each B scan is passed through different CNN like that, and Fisher extraction, so that way we get the Fisher, and there is a attention model. There is a this attention weights will be obtained, and it will be multiplied, and then that's like in the case of we illustrated the mechanism of attention, so it will be Fishers will be weighted by the attention weight, and then it will be classified. Okay, so it will be classified, so that essentially there will be Fisher extraction, and these Fishers from the Fisher map itself, attention weights will be also obtained, and those attention weights will multiply the Fisher maps, and then classification will be done using the fully connected neural network. Okay, and soft mesh activation, so that way it can be applied. So the proposed BSCNN method automatically encodes discriminative information from clinically relevant B scans to make diagnostic decision for the volume using the attention mechanism. So that way, this is illustrated here, which part is given more importance. So that way, it is seen that actually clinically important parts are given more weights like that. Okay, this is the scale. So that way, this is a high weight like that. So this network gives importance to clinically important B scans. So that way, these are some applications. To sum up what we have done, we introduced expert systems for healthcare. discuss the basics of machine learning and deep learning, explains the basic ANN and CNN architecture and underlying mathematics, introduce some of the recent research on OCT-based medical diagnosis. Okay, thank you. Okay, so here I stop my presentation. So you have any question?
Participants, please ask your questions. Participants, please ask your questions. If you have any queries. Sir, there is a question in the chat box.
Okay. So chat box.
Sir, right hand side corner.
Right hand side corner. No.
That one. Yes.
Okay.
Last one, sir.
Sir, can this slide be shared on our email? Okay, we'll share it. Kindly share the PPT. Okay.
And, sir, last one.
Is there any model to predict bedtime of patient admitted in ICU, CCU? No, I am not aware of. Actually, though I have presented these things, but I am not a strict researcher in biomedical. So that way, I am not aware of that type of research. Is there possible to detect model to apply to which? So then Rajesh question, Satish Shekhar, is there possible to detect heart defects in newborn? Yeah, that is possible. I think that is from fetal, from the suppose mother's ECG itself, fetal ECG can be obtained. There are separate techniques, so that way maybe it can be done. So how to detect this fetal ECG from the mother's ECG, that is also a very well researched area, and those fetal ECG can be used. Then how do we know which model to apply to which model? So this is normally by analogy only. Suppose most of the models are developed for image processing or computer vision application, and somehow you have to map your problem to that type of problem, and then you can suppose what is the most recent model, because your goal is to suppose when we are applying a deep learning model, model should be number of trainable parameters should be less, and as well as classification is should be better, and then these are the things you have to see, and then transfer learning, because you cannot train the network, because it requires a lot of data. For example, if we consider the image net data, millions of data are there, images are there. So that way, you have to see that at least the transfer learning model you can apply. Okay. So similarly, other question is detecting congenital heart defects in fetal is better after baby, or after baby born is better. That question I will not be able to answer. Okay, these are some of the questions.
Hello, good afternoon, sir. Sandeep here.
Okay.
Sir, I have a question. Sir, in CNN, the use of ReLU will minimize the vanishing gradient problem,
Yeah, that is
ReLU
one.
activation function.
Yeah.
But like, is there any exploding gradient problem in CNN? If it is there, like, how is it overcome, sir?
No, even like that ResNet and all, that skip connection is one way to avoid both the problems. Because it is again initialized. Skip connection is like again you are initializing the network like that, no? Because one part is again connected as it is without going through the intermediate layer. So that way, that is one way.
Okay, sir. Thank you, sir. Thank you, sir.
Okay.
Are there any more questions, participants? Please ask. I hope there are no further questions. So let us conclude the session here. Sir, thank you very much for joining with us and sharing your knowledge and guiding us for artificial intelligence, how to use it for different aspects and mainly for healthcare systems. And we are very much fortunate to learn from you and from the entire team, Gauhati University. I thank you for being with us. Thank you very much, sir.
Okay. I also thank you for giving this opportunity. Goodbye.